Welcome to the Deep Dive, where we explore intriguing corners of knowledge. This is another installment in our series venturing into the vast landscape of the online encyclopedia of integer sequences, the OEIS.
It's always a pleasure. And yeah, for number theory students listening, the OEIS is just, well, an incredible resource. So many connections waiting to be found.
Absolutely. Today, we're zeroing in on a sequence that might sound a bit technical, 8000184. The description, genus-zero rooted maps with three faces.
Right. And let's be clear from the start, when we say maps, we're not talking about geography here. Forget Google Maps for a bit.
Yeah, definitely not that kind. So our mission for this deep dive is pretty clear, right? First, we need to unpack what these genus-zero rooted maps with three faces actually are.
Exactly. And second, and this is maybe more crucial for the number theory folks, why should you care? Why is this sequence, this type of object, important or interesting in the grand scheme of mathematics?
So think of this as a sort of quick but insightful introduction.
Precisely. A starting point.
Okay, let's jump in. The map part. If it's not geographical, what is it in, this mathematical context?
Right. So in combinatorics, a map is basically a way to draw a graph dots and lines onto a surface. It divides the surface up into regions or faces.
Okay, drawing a graph on a surface?
Yeah, but we can define it more formally using permutations. It sounds abstract, but bear with me. Imagine you have a bunch of, say, tunelar half edges.
Half edges?
Yeah, think of an edge as joining two of these. So we use a permutation, let's call it alpha, to pair these half edges up. Alpha swaps pairs. Do it twice. You're back where you started. It's an involution with no fixed points. Every half edge gets paired.
Okay, so alpha makes the edges by pairing these halves. Got it. What about the dots and regions, the vertices and faces?
Good question. We need two more permutations. There's beta. This one tells you the order of half edges cycling around each vertex. Imagine standing at a vertex. Beta tells you the next half edge in, say, counterclockwise order.
All right, beta for vertices.
And then there's gamma. Gamma defines the boundaries of the faces. And the cool part is how they relate. Data followed by alpha equals gamma. So going around a vertex and then along an edge actually traces the boundary of a face.
Whoa. Beta, alpha, gamma. That connects everything.
Exactly. And the number of cycles in alpha, beta, and gamma tells you the number of edges, vertices, and faces, respectively.
Huh. That's clever. Is there anything else to the definition?
Just one more key thing. The group generated by these three permutations, alpha, beta, gamma, needs to act transitively on the set of half edges.
Transitive, meaning?
It basically means the map is connected. You can get from any half edge to any other by following the rules of alpha, beta, and gamma. It's not in separate, disconnected pieces.
Okay, this is a very algebraic way to define something visual.
It is. But it's incredibly powerful for studying these structures, especially for counting them. Maybe a tiny example. A single loop on a sphere. One edge, one vertex, two faces, technically, inside and outside, two half edges. Alpha swaps them. Delo just cycles the one vertex. Gamma handles the two faces. It's simple, but it shows how permutations encode the structure.
Right, I can sort of picture that. Now, the description says genus-zero. What's genus?
Genus is about the surface the map is drawn on. Think topology. It's related by the Euler characteristic formula. Number of vertices minus number of edges plus number of faces equals $2 the genus.
VE plus F equals 2G2.
Okay, so G just tells you kind of how many holes or handles the surface has. A sphere has no handle, so its genus is 0. A donut or torus has one handle, its genus is 1.
Ah, so genus-zero means our maps are drawn on a sphere.
Yeah.
Or something equivalent, like a flat plane.
Exactly. We're talking about planar maps, maps you can draw on paper without edges crossing.
And for these genus-zero maps, the formula simplifies. Since genus is times...
Precisely. VE plus F equals 2. A fundamental relationship for planar graphs.
Okay, planar maps. Next up, rooted. What does rooting a map mean?
Rooting is a common trick in enumeration, in counting things. We pick one specific edge, give it a direction, and choose one side of that directed edge. It's like putting a little flag on one part of the map.
A flag? Why do we need to do that? What's the point?
It's all about symmetry. Imagine two maps that look the same if you just rotate one. Are they really different maps? For counting unique structures, we want to count them as one.
Okay.
Rooting breaks that symmetry. By choosing a specific rooted edge direction side combination, each structurally distinct map gets a unique marker. It stops us from counting the same map multiple times just because it looks the same from different angles.
Ah, I see. It gives each map a unique starting point, sort of. Prevents overcounting due to rotations or flips.
Exactly that. It makes the counting problem manageable.
Makes sense. So planar maps uniquely identified by a root, and finally with 3 faces.
This just pins down the number of regions the map divides the plane or sphere into, exactly 3 distinct areas.
Okay, so if we take the planar map formula, VLN E plus F equals 2, 2, and we plug in phi AP3.
We get VLE plus 3 equals 2, 2.
Which rearranges to 1 deal equals V plus delta 1.
Bingo. So these specific maps we're looking at genus-zero 3 faces always have exactly 1 more edge than they have vertices. It's a built-in property.
That's neat. A simple structural constraint pops right out. So putting it all together, we're counting connected drawings on a sphere marked with a special root edge that divide the sphere into 3 regions and always have vital plus plus 1 in edges.
You've got it. And sequence A000184 in the OEIS is that count.
So the first term is the number of these maps with 1 edge, the second term is the count for 2 edges, and so on.
Precisely. The naughth term counts the maps with null edges and necessarily null 1 vertices and 3 faces.
Okay, it's concrete now. But back to the why care part, especially for number theory students. It still feels a bit graph theoretic, combinatorial.
It absolutely is combinatorial at heart. But the connections, they sneak up on you. Think about how we count these things. Often we use generating functions.
Generating functions,
Yeah.
power series where coefficients count things.
Exactly. You build a power series where the coefficient of 6 nullers is the number of maps with no edges. Finding and analyzing these generating functions often requires tools from complex analysis or solving algebraic functional equations. These are tools and techniques that are bread and butter in analytic number theory, for instance.
So the sequence itself, A000184, is like a shadow cast by these more complex mathematical objects and the functions describing them.
That's a great way to put it. The sequence encodes information that's often accessed via these more advanced tools. Plus, map enumeration connects to graph theory, obviously, but also things like group theory when you consider the symmetries we mentioned. Both fields have significant overlaps with number theory.
You mentioned specific techniques, cut equations, bijections.
Yeah.
Are those important here?
Very much so. The Tutte equation, for example, is a cornerstone method. It sets up a functional equation for the generating function. Solving it can be tricky, involving things called catalytic variables, but it's powerful.
And bijections.
Bijections are kind of the holy grail sometimes. If you can find a direct one-to-one mapping between our maps, rooted planar 3 faces, and some other combinatorial objects that we already know how to count easily, then you get the formula almost for free.
And potentially understand the structure better.
Definitely. Bijective proofs are often very insightful. They show why 2 different sets of things have the same size by explicitly pairing them up.
It really does sound like these maps, while simple to describe visually, sit at a crossroads of different mathematical ideas.
They really do. Topology, combinatorics, algebra, analysis, they all come together. And sometimes studying these map counts reveals unexpected patterns or connections relevant elsewhere, maybe even number theory. There are also links to models in statistical physics, like random planar maps. It's a surprisingly rich area.
This has been really illuminating. So A000184 isn't just some obscure list of numbers.
Not at all. It counts these specific rooted planar maps with 3 faces. And understanding how to count them and the properties of the sequence itself involves techniques and concepts relevant across mathematics.
So the main takeaway is that A000184 counts these specific combinatorial objects, rooted planar maps with 3 faces, and connects to fundamental ideas in topology, combinatorics, and the analytical algebraic methods used for enumeration.
That's a good summary. It's a window into a larger world.
We definitely encourage listeners to look up A000184 on the OEIS, see the numbers, the formulas, follow the links, and maybe check out resources like that Introduction to Map Enumeration if you want to dive deeper into Tutte's methods or bijections.
Absolutely. And maybe a final thought to leave with. The OEIS has thousands upon thousands of sequences. How many other entries described in just a few words hide similarly deep connections? What other combinatorial counts might unexpectedly relate to patterns in prime numbers or elliptic curves or whatever you're studying?
A great question to ponder. It highlights the interconnectedness of mathematics. Thank you for joining us on this deep dive.